Welcome to the presentation on bearings and failure modes.
Greetings to everyone. I am Kishore Kumar Aguna. I have 10 plus years industrial experience and worked in various mechanical engineering disciplines such as non-destructive testing, welding inspection, and condition-based maintenance. As of now, I am working independently and associate with various organizations who are involved in testing, commissioning, and plant reliability maintenance tasks. I would like to share my working experience and knowledge and notes prepared from internet, various books. This presentation particularly prepared on machinery bearings, types, and various failure modes involved, root causes, and various technologies involved to diagnose bearing issues and some precautions we have to take to solve these bearing issues.
What is a bearing? The term bearing is derived from the verb to bear, a bearing being a machine element that allows one part to bear, to support another. A bearing is a machine element that constrains relative motion to only the desired motion, and reduces friction between moving parts. The design of the bearing may, for example, provide for free linear movement of the moving part or for free rotation around a fixed axis, or it may prevent a motion by controlling the vectors of normal forces that bear on the moving parts. Most bearings facilitate the desired motion by minimizing friction. Bearings are classified broadly according to the type of operation, the motions allowed, or to the directions of the loads, forces, applied to the parts. Bearings types. There are several types of bearings, designed for specific applications and designed to withstand specific types of loads, thrusts or radial. The most popular types of bearings are ball bearings, tapered rolling element bearings, thrust bearings, journal bearings, airfoil bearings, linear bearings, magnetic bearings, etc. When selecting a bearing for a particular application, there are several considerations to keep in mind, including bearing friction, temperature, and lubrication. Along with the specific design and construction of the bearing, these three interacting factors can affect the overall performance. Rolling element bearings. Rolling element bearings have been widely used in rotating equipment. They are designed to carry load and provide constrained motion between two or more parts. A rolling element bearing consists of outer race, rolling elements, balls, cylindrical roller, etc., inner race, and a cage to support and guide the rolling elements. Below are common types of rolling element bearings. 1. Spherical roller bearings. 2. Self-aligning ball bearings. 3. Deep groove ball bearings. 4. Cylindrical roller bearings with cage. 5. Spherical roller bear dottings. 6. Needle roller bearings. Rolling element bearings designation system. For example, RNU 2306CM C3S1. Here R is prefix and U is bearing type series, 2 is bearing width/height series, 3 is diameter series, 06 is bearing bore C3S1 is suffix. The first letter, not the prefix, represents the bearing type 0 angular contact ball bearings, double row 1 self-aligning ball bearings, 2 spherical roller bearings and spherical roller thrust bearings, 3 taper roller bearings, 4 deep groove ball bearings, double row 5 thrust ball bearings, 6 deep groove ball bearings, single row 7 angular contact bearings, single row 8 cylindrical roller thrust bearings and cylindrical roller bearings. N equals outer ring no groove, nu equals inner ring no groove, and J equals only one shoulder on inner groove. Nup equals only one shoulder on inner groove plus one loose inner flange.
Rolling element bearings designation system. Here first table 1 refers to code for bearing bore normally, number X5 equals bore. For example, bearing bore reference number 3 to 9 is bore 3 to 9 mm, 00 is 10 mm, 01 is 12 mm, 02 is 15 mm, 03 is 17 mm, 04 is 20 mm, 96 is 480 mm, 500 is 500 mm, 530 is 530 mm. Second table is codes for special design characteristic. A refers to new modified model. B internal design. DA supply in a ring. E reinforced design. K tapered bore 112. K 30 tapered bore 130. N groove for snap ring. Outer ring RSR with 1 seal. 2 RSR with 2 seals. S lubrication groove and holes. Outer ring ZR with 1 dust shield. 2 ZR with 2 dust shield. Rolling element bearings. Designation system suffix for cage design. The cage suffixes P, H, A, B are often added to the material code. F machine steel cage. L machine light metal cage. M machine brass cage. T machine cage of laminated textile. TB cage of polyamide. J press steel cage. Y pressed brass cage. P window type cage. H snap type cage. A outer lip riding. B inner lip riding. Code for accuracy and bearing clearance. Precision and clearance are often combined. For example, P52 equals precision P5 and clearance C2. P6 tolerance less than PN, PO. P5 tolerance less than P6. P4 tolerance less than P5. P4S reduced. P4 tolerance. P2 special precision. SP ultra precision. C1 bearing clearance less than C2. C2 bearing clearance less than CN, CO. C3 bearing clearance. C4 bearing clearance greater than C3. C5 bearing clearance greater than C4. Special codes. For example, for heat treatment S1 to S4 special heat treatment, dimensionally stable above 150 degrees Celsius. Rolling element bearings designation system. For bearing number 6206 first number deep groove ball bearing, single row second number width series, 2/3 number diameter series, 0/4 number bore hole, 6x5 equals 30 mm. For bearing number 7305 first number angular contact bearing, single row second number width series, 3/3 number diameter series, 0/4 number bore hole, 5x5 equals 25 mm. For bearing number 30209 first number taper roller bearing second number width series, 0/3 number diameter series, 2/4 number bore hole, 9x5 equals 45 mm. For bearing number new 417 first number cylindrical roller bearing fourth number bore hole, 17x5 equals 85 mm. Nuno flange on inner ring. Flange on outer ring.
Here we can see the below table about various bearing types and applications. Here we can see the below table about various conditions effects on bearings.
Plain bearings. All plain bearings also are referred to as fluid film bearings. In addition, radial plain bearings also are commonly referred to as journal bearings. Plain bearings are available in a wide variety of types or styles and may be self-contained units or built into a machine assembly. Plain bearings are dependent on maintaining an adequate lubricant film to prevent the bearing and shaft surfaces from coming into contact, which is necessary to prevent premature bearing failure. However, this is difficult to achieve, and some contact usually occurs during operation. Material selection plays a critical role in the amount of friction and the resulting seizure and wear that occurs with surface contact. Note that fluid film bearings do not have the ability to carry the full load of the rotor assembly at any speed and must have turning gear to support the rotor's weight at low speeds. Thrust bearing. Thrust plain bearings consist of fixed shaft shoulders or collars that rest against flat bearing rings. The lubrication state may be semi-fluid, and friction is relatively high. In multicolor thrust bearings, allowable service pressures are considerably lower because of the difficulty in distributing the load evenly between several collars. However, thrust ring performance can be improved by introducing tapered grooves. Elliptical bearings. The elliptical bearing is oil lubricated and typically is used in gear and turbine applications. It is classified as a lobe bearing in contrast to a grooved bearing. Where the grooved bearing consists of a number of partial arcs with a common center, the lobe bearing is made up of partial arcs whose centers do not coincide. The elliptical bearing consists of two partial arcs where the bottom arc has its center a distance above the bearing center. This arrangement has the effect of preloading the bearing, where the journal center eccentricity with respect to the loaded arc is increased and never becomes zero. Partial arc bearing. A partial arc bearing is not a separate type of bearing. Instead, it refers to a variation of previously discussed bearings, for example, grooved and lobed bearings, that incorporates partial arcs. It is necessary to use partial arc bearing data to incorporate partial arcs in a variety of grooved and lobed bearing configurations. Tilting pad bearings. Tilting pad bearings are widely used in high-speed applications where hydrodynamic instability and misalignment are common problems. This bearing consists of a number of shoes mounted on pivots, with each shoe being a partial arc bearing. The shoes adjust and follow the motions of the journal, ensuring inherent stability if the inertia of the shoes does not interfere with the adjustment ability of the bearing. The load direction may either pass between the two bottom shoes or it may pass through the pivot of the bottom shoe. The lubricant is incompressible, i.e., liquid, and the lubricant film is laminar. Bearing selection guide for particular performance requirements. Bearing selection guide for particular performance requirements. Bearing selection guide for particular performance requirements. Plain bearing selection guide. Thrust bearing selection guide. Magnetic bearing. Magnetic bearings are devices used to support, levitate, objects using magnetic forces. Some magnetic bearings provide a full non-contact support of an object, whereas others provide only a partial support working together with more conventional mechanical bearings. While a wide variety of magnetic bearings have been developed, only one type has been widely accepted in the industry so far: active magnetic bearings, AMBs. This is because an active magnetic bearing can exert higher density forces on surfaces of supported objects than any other type of magnetic bearing. They can also operate in a wide range of environments and their properties can be made highly configurable through software parameters. Foil bearing. A foil bearing, also known as a foil air bearing, is a type of air bearing. A shaft is supported by a compliant, spring-loaded foil journal lining. Once the shaft is spinning fast enough, the working fluid, usually air, pushes the foil away from the shaft so that no contact occurs. The shaft and foil are separated by the air's high pressure, which is generated by the rotation that pulls gas into the bearing via viscosity effects. A high speed of the shaft with respect to the foil is required to initiate the air gap, and once this has been achieved, no wear occurs. Unlike aerostatic or hydrostatic bearings, foil bearings require no external pressurization system for the working fluid, so the hydrodynamic bearing is self-starting. Linear motion bearings. A linear motion bearing or linear slide is a bearing designed to provide free motion in one direction. There are many different types of linear motion bearings. Motorized linear slides such as machine slides, XY tables, roller tables and some dovetail slides are bearings moved by drive mechanisms. Not all linear slides are motorized, and non-motorized dovetail slides, ball bearing slides and roller slides provide low-friction linear movement for equipment powered by inertia or by hand. All linear slides provide linear motion based on bearings, whether they are ball bearings, dovetail bearings, linear roller bearings, magnetic or fluid bearings. XY tables, linear stages, machine slides and other advanced slides use linear motion bearings to provide movement along both X and Y multiple axes. Bearings damage analysis. If you're concerned that your bearing is deteriorating, look for the following signs: vibrations, whether felt by hand or measured with a frequency analyzer; abnormal noises, displacement of rotational centerline; running temperature increase; odd smells, lubricant deterioration; lubricant leakage, visual discovery during routine maintenance check. In some cases, the cause is contact fatigue, inclusion origin, point surface origin, geometric stress concentration and microspalling. In 90% of the cases, though, the cause is non-fatigue factors, including foreign materials, corrosion, inadequate lubrication, improper handling, bad running conditions, types of bearing damage, wear, abrasive contamination. Fine foreign material in the bearing can cause excessive abrasive wear. Sand, fine metal from grinding or machining, and fine metal or carbides from gears wear or lap the rolling elements and races. In tapered bearings, the roller ends and cone rib wear to a greater degree than the races. This wear causes increased end play or internal clearance, which can reduce fatigue life and create misalignment in the bearing. Abrasive wear also can affect other parts of the machine in which the bearings are used. The foreign particles may get in through badly worn or defective seals. Improper initial cleaning of housings and parts, Ineffective filtration or improper filter maintenance can allow abrasive particles to accumulate. Types of bearing damage: wear, pitting and bruising. Hard particles rolling through the bearing may cause pitting and bruising of the rolling elements and races. Metal chips or large particles of dirt remaining in improperly cleaned housings can initiate early fatigue damage. Common external debris contaminants include dirt, sand and environmental particles. Typical causes of internal debris contamination include wear from gears, splines, seals, clutches, brakes, joints, improperly cleaned housings, and damaged or spalled components. These hard particles travel within the lubrication, through the bearing and eventually bruise, dent, the surfaces. Raised metal around the dents acts as surface stress risers to cause premature spalling and reduce bearing life. Types of bearing damage: wear, grooving. Extremely heavy wear from chips or metal particles can cause grooving. These contaminants become wedged in the soft cage material and cut grooves in the rolling elements. This condition generates improper rolling contact geometry and can reduce service life. Types of bearing damage: etching, corrosion. Etching, or corrosion, remains one of the most serious problems anti-friction bearings encounter. Without adequate protection, the high degree of surface finish on races and rolling elements makes them susceptible to corrosion damage from moisture and water. Etching is most often caused by condensate collecting in the bearing housing from temperature changes. Moisture or water can get in through damaged, worn or inadequate seals. Improperly washing and drying bearings when you remove them for inspection also can cause considerable damage. After cleaning and drying or preparing bearings for storage, you should coat them with oil or another preservative and wrap them in protective paper. You should always store bearings, new or used, in a dry area and keep them in original packaging to reduce the risk of static corrosion appearing before mounting. Types of bearing damage: inadequate lubrication. Inadequate lubrication can create a wide range of damage conditions. Level 1, discoloration. Metal-to-metal contact results in excessive bearing temperature. High temperatures result in discoloration of the races and the roller. In mild cases, the discoloration is from the lubricant staining the bearing surfaces. In severe cases, the metal is discolored from high heat. Level 2, scoring and peeling, insufficient or complete lack of lubricant. Selecting the wrong lubricant or lubrication type. Temperature changes. Sudden changes in running conditions. Types of bearing damage: inadequate lubrication. Inadequate lubrication can create a wide range of damage conditions. Level 3, excessive roller end heat. Inadequate lubricant film results in localized high temperatures and scoring at the large ends of the rollers. Level 4, total bearing lockup. High localized heat produces metal flow in bearings, altering the original bearing geometry and the bearing's material. This results in skewing of the rollers, destruction of the cage, metal transfer and complete seizure of the bearing. Types of bearing damage: fatigue spalling. Spalling is the pitting or flaking away of bearing material. Spalling primarily occurs on the races and the rolling elements. Geometric stress concentration, GSC, spalling. Causes for this type of damage mode include misalignment, deflection or edge loading that initiates high stress at localized regions of the bearing. It occurs at the extreme edges of the race/roller paths. It also can be the end result of shaft or housing machining errors. Types of bearing damage: fatigue spalling. Point surface origin, PSO, spalling. Very high and localized stress generates this type of damage mode. The spalling damage is typically from nicks, dents, debris, etching and hard particle contamination in the bearing. It's the most common type of spalling damage, and it often appears as arrowhead-shaped spalls, propagating in the direction of rotation. Types of bearing damage: fatigue spalling. Inclusion origin spalling. This damage occurs when there's bearing material fatigue at localized areas of subsurface, non-metallic inclusions following millions of load cycles. A sign of this damage appears in the form of localized, elliptically shaped spalls. Due to the improvement of bearing steel cleanness during the past 2 decades, it may be unlikely you will encounter this type of spalling. Types of bearing damage: excessive preload or overload. Excessive preload can generate a large amount of heat and cause damage similar in appearance to inadequate lubrication damage. Often the two causes may be confused, so you need to check the bearing thoroughly to determine the root problem. A lubricant that's suitable for normal operation may be unsuitable for a heavily preloaded bearing, as it may not have the film strength to carry the very high loads. The lubricant breakdown in high preloads can cause the same type of damage. Another type of damage can result from heavy preloads even if you use a lubricant, such as an extreme pressure type of oil, that's engineered to carry heavy loads. Although the lubricant can handle the loads so that there's no rolling element or race scoring, the heavy loads may cause premature subsurface fatigue spalling. Types of bearing damage. Excessive end play. Excessive end play results in a very small load zone and excessive looseness between the rollers and races outside the load zone. This causes the rollers to unseat, which leads to roller skidding and skewing as the rollers move into and out of the load zone. This movement creates scalloping in the cup race, and cage wear from excessive roller movement and the impact of the rollers with the raceway. Types of bearing damage. Misalignment and inaccurate seat and shoulder machining. Misaligned bearings will shorten bearing life. This reduction depends on the degree of misalignment. To gain more life from the bearing, the seats and shoulders supporting the bearing must be within the specified limits set by the bearing manufacturer. If the misalignment exceeds those limits, the load on the bearing won't be distributed along the rolling elements and races as intended. Instead, it will be concentrated on only a portion of the rollers or balls and races. In cases of extreme misalignment or off angle, the load will be carried only on the extreme ends of the rolling elements and races. A heavy concentration of the load and high stresses at these points will cause early metal fatigue. Types of bearing damage. Handling and installation damage. You have to be careful when handling and assembling bearings so that you don't damage the rolling elements, race surfaces and edges. Deep gouges in the race surface or battered and distorted rolling elements will make metal rise around the gouged or damaged area. High stresses will occur as the rolling elements go over these surfaces, creating premature, localized spalling. The immediate effect of these gouges and deep nicks will be roughness, vibration and noise in the bearing. Types of bearing damage. Damaged bearing cages or retainers. Careless handling and using improper tools during installation may cause cage or retainer damage. Cages or retainers are usually made of mild steel, bronze or brass and can be easily damaged, which can cause premature bearing performance problems. In some applications, environmental and operating conditions can cause fractured cages or retainers. This type of damage is too complex to cover in this reference guide. If you experience this problem, contact your Timken sales or service engineer. Types of bearing damage. High spots and fitting practices. Careless handling or damage caused when driving outer races out of housings or wheel hubs can create burrs or high spots in the outer race seats. If a tool gouges the housing seat surface, it will leave raised areas around the gouge. If you don't scrape or grind down these high spots before reinstalling the outer race, the high spot will transfer through the outer race and cause a corresponding high spot in the outer race's inside diameter. Stresses increase when the rolling elements hit this high area, which can result in lower than predicted service life. Types of bearing damage. Improper fit in housings or shafts. In general, we should apply the bearing race, where the rotating load exists, with a press or tight fit. An example is a wheel hub, where the outer race should be applied with a press foot. The races on a stationary axle would normally be applied with a light or loose foot where the shaft rotates. The inner race should normally be applied with a press foot and the outer race may be applied with a split foot or even a loose foot, depending on the application. Types of bearing damage. Brinell and impact damage. Improper mounting and disassembly methods and/or extremely high operational impact or static loads may cause brinelling. Brinell from improper assembly and disassembly happens when a force gets applied against the unmounted race. When mounting a bearing on a shaft with a tight foot, pushing the outer race will exert an excessive thrust load and bring the rolling elements into sharp contact with the race, causing brinell. Types of bearing damage. False brinelling. As the name indicates, false brinelling isn't true brinelling or denting. It's actually fretting wear caused by slight axial rolling element movements while the bearing is stationary. Vibration can make the rolling element slide back and forth across the race, wearing a groove into the race. You can distinguish false brinelling from true brinelling by examining the depression or wear area. False brinelling will actually wear away the surface texture, whereas the original surface texture will remain in the depression of a true brinell. Types of bearing damage. Burns from electric current. Arcing, which produces high temperatures at localized points, occurs when an electric current that passes through a bearing is broken at the contact surfaces between the races and rolling elements. Each time the current is broken while passing between the ball or roller in race, it produces a pit on both parts. Eventually fluting develops. As it becomes deeper, it creates noise and vibration. A high amperage current, such as a partial short circuit, will cause a rough, granular appearance. Heavy jolts of high amperage charges will cause more severe damage, welding metal from the race to the ball or roller. These metal protrusions on the roller will, in turn, cause a crater effect in the race, generating more noise and vibration. Types of bearing damage: cam fracture, wide inner ring ball bearings. An undersized shaft or an outer ring that cannot be aligned due to the housing may cause a broken cam, a misaligned travel path, or bearing wobble. This type of bearing damage may be prevented by using the correct size shaft and by using the Timken self-aligning feature, a spherical outer ring to compensate for initial misalignment and correctly mount bearings. Types of bearing damage: voids and electrical pitting. Electrical pitting appears as rounded pits in the bearing lining. The pits may appear frosted or they may be blackened due to oil deposits. It is not unusual for them to be small and difficult to observe with the unaided eye. A clearly defined boundary exists between the pitted and unpitted regions, with the pitting usually occurring where the oil film is thinnest. Electrical pitting damage is caused by intermittent arcing between the stationary and rotating machine components. Because of the small film thicknesses relative to other machine clearances, the arcing commonly occurs through the bearings. Although the rotating and other stationary members can also be affected, the most severe pitting occurs in the soft babbitt. Electrical pitting can be electrostatic or electromagnetic in origin. Although both sources result in pitting damage, they differ in origin and destructive capabilities. Types of bearing damage: fatigue. Fatigue damage may represent itself as intergranular or hairline cracks in the babbitt. The cracks may appear to open in the direction of rotation. Pieces of babbitt may fall out or appear to be pulled away in the direction of rotation. A combination of causes contributes to fatigue damage, but concentrated cyclic loading is usually involved. The fatigue mechanism involves repeated bending or flexing of the bearing, and damage occurs more rapidly with poor bonding. It is important to note that fatigue damage will occur without poor bonding. Fatigue can occur when conditions produce concentrated cyclic loads, such as misalignment, journal eccentricity, imbalance, bent shaft, thermal cycling, vibration. Types of bearing damage: cavitation. Cavitation damage appears as discrete irregularly shaped babbitt voids which may or may not extend to the bond line. It may also appear as localized babbitt erosion. Often called cavitation erosion, cavitation damage is caused by the formation and implosion of vapor bubbles in areas of rapid pressure change. Damage often occurs at the outside diameter of thrust bearings due to the existence of higher velocities. Types of bearing damage: erosion. Erosion damage may appear as localized babbitt voids with smooth edges, particularly in the direction of rotation. Damage is more likely to occur in stationary members. As a rule of thumb, if the babbitt has been affected, the cause was cavitation damage, not erosion. Because erosion is caused by sudden obstructions in oil flow, it is more likely to occur in other areas, because the babbitt is under high pressure. Once damaged, however, babbitt erosion may occur. Types of bearing damage: corrosion. Corrosion damage is characterized by the widespread removal of the bearing lining by chemical attack. This attack produces a latticework appearance. The damage may be uniform with the affected elements being washed away, leaving the corrosion-resistant elements behind. Corrosion may also affect the rotating collar, runner or journal, appearing as random, widespread rust or pitting. The pits are easily distinguished from electrical pitting, because they are not as uniform or smooth-bottomed. Types of bearing damage: collar/runner/journal surface. The most commonly overlooked bearing component is the collar. It is the single most important part of the bearing. Collar rotation draws oil into the region between the collar and shoe surfaces. Oil adheres to the collar and is pulled into pressurized oil wedges. It is important that the collar faces be parallel and perpendicular to the center line of the shaft. If the collar is not within tolerance, the resultant wobble will force the shoes and leveling plates to constantly equalize, causing rapid leveling plate wear. Understanding bearing life. Bearing service life. Bearing service life is based on many factors. Depending on the application requirements, the actual service life can greatly vary. Reduced service life can be caused either individually or by any combination of faulty mounting, poor housing support, improper adjustment, high static misalignment or shaft and housing deflection, insufficient lubrication, contamination, poor or inconsistent maintenance practices, improper or abusive handling. The life of your bearing also depends on the load zone obtained under operating conditions. Generally speaking, the greater the load zone, the longer the life of the bearing under stabilized operating conditions. Factors that impact lubrication performance. Inadequate lubrication causes a high percentage of bearing damage. Although it's a broad term, we classify inadequate lubrication into these basic categories: overfilling, incorrect grease, worn-out grease, incorrect lubrication systems and intervals. Underfilling, mixing greases, water contamination. Factors that impact lubrication performance. Overfilling. Overfilling a bearing with too much grease can cause excess churning and high temperatures during operation. This can create overheating and excess grease purging, leaking. See note below. Overheating happens when the generated heat can't dissipate correctly, continually building until damage occurs. As the bearing's operating temperature rises, the oxidation, breakdown, rate of the grease sharply increases, doubling every 10 degrees Celsius/18 degrees Fahrenheit. Factors that impact lubrication performance. Underfilling. Underfilling a bearing with grease also can have adverse consequences. As in overfilling, underfilling can generate heat but for different reasons. A low amount of grease can create a condition known as a grease starvation, which causes heat generation or excessive metal wear during operation. If a bearing suddenly becomes noisy and or the temperature increases, excessive wear may be taking place. Factors that impact lubrication performance. Incorrect grease. The base oil in a particular grease may have a different thickness, viscosity, than what's recommended for your application. If the base oil viscosity is too heavy, the rolling elements may have difficulty pushing through the grease and begin to skid. If this happens, excessive grease oxidation, breakdown, may cause premature grease degeneration and excessive wear of bearing components. If the viscosity is too light, the thin lubricant film from the higher temperatures may cause peeling, microspalling, and wear. Additionally, the additives contained in a particular grease may be inappropriate or even incompatible with the surrounding components in your system. Factors that impact lubrication performance. Mixing greases. A bearing should run well with the correct grease. When performing routine maintenance, make sure that you lubricate the bearing with the same type of grease or a compatible substitute. If you use an incompatible grease, or one with the wrong consistency, this new mixture may 1. Soften and leak out of the bearing because of the incompatibility of the grease thickener. 2. Become lumpy, discolored and hard. Factors that impact lubrication performance. Worn out grease. Grease is a precise combination of additives, oil and thickener. It acts like a sponge to retain and release the oil. Time and temperature conditions can deplete oil release properties. When this occurs, the grease is worn out. Factors that impact lubrication performance. Incorrect lubrication systems and intervals. To help prevent bearing components from wearing prematurely, it's critical to maintain the correct bearing lubrication systems and intervals. If you don't follow maintenance schedules, excessive oxidation may cause the lubrication to deteriorate. Factors that impact lubrication performance. Water contamination. The effect of water on grease by comparing fresh grease to a grease emulsified with 30% water. The fresh grease is smooth and but tarry compared to the water-laden grease, which has a milky white appearance. The presence of as little as 1% water in grease can make a significant impact on bearing life. Bearings condition monitoring and failure diagnosis. Vibration analysis. Vibration analysis is a very powerful technology. It can be used to detect a wide range of fault conditions in rotating machinery, including defects in rolling element bearings. Vibration analysis can be used to detect the root causes of bearing failure and the symptoms of bearing failure. But it should be noted that the best strategy of every condition monitoring technician is to utilize as many techniques as possible in order to gain the greatest confidence in any fault diagnosis. It is recognized that other technologies exist, including oil analysis, wear particle analysis and ultrasound monitoring, all of which can aid in the detection of rolling element bearing faults. Bearings condition monitoring and failure diagnosis. Ultrasound analysis. Ultrasound is considered the most versatile predictive technology in the toolbox. Some revere ultrasound as their frontline defense against premature machine failures. Ultrasound's simplicity, economics and broad spectrum of applications has led one clever company to christen the technology predictive maintenance for the masses. Today, Ultrasound fulfills the necessary task identifying early fault conditions in rotating and non-rotating machinery. As a companion technology to vibration analysis, ultrasound lends a symbiotic and complementary air. Bearings condition monitoring and failure diagnosis. Lubricant analysis. Lubricant analysis is one of the oldest technologies that is still currently applied. A lubricant's function is to control friction, wear, corrosion, temperature and contaminants as well as transmit power. Simply put, the objective should be to preserve a clean, cool and dry environment. This is achieved by maintaining the condition of the lubricant, the lubrication system and the machine. Lubricant analysis can be broken down into grease and oil, with 3 specific focus groups: fluid properties, contamination and wear debris. Several different tests can be performed in each group, depending on the conditions mentioned above. Some of the most common tests performed on a routine basis are viscosity, moisture content and particle count. Bearings condition monitoring and failure diagnosis. IR thermography. Infrared thermography is often used to locate suspected problems in bearings, which can then be confirmed with other technologies. Inspecting bearings is another useful application for infrared thermography. Abnormal friction within a bearing, generating heat, causes the bearing's surface temperature to rise. This thermal signature, when detected, is an indication of a potential bearing problem, anything from under-lubrication, over-lubrication, poor maintenance or simply a bad bearing. Infrared is especially helpful for inspecting low-speed equipment, including overhead conveyors or idlers, quickly and easily. Bearings condition monitoring and failure diagnosis. Acoustic emission. Acoustic emission has the ability to detect the initial phase of component degradation. Moreover, it has been observed that vibration analysis is not as successful at low rotational speeds, below 100 revolutions per minute. This because the energy generated within this speed region is not detectable using conventional vibration.
Finally, we reached end of this presentation. In many cases involving bearing selection during the initial design of a machine, obtaining a satisfactory rating life is the prime consideration. Once the loads and speeds have been determined, the question now becomes how many hours of rating life are needed for a well-designed machine. Sometimes this is spelled out either by specific industry standards or company policy based on the industry and customers' expectations. The health of your bearing is critical to the health of your equipment and process. With proper performance monitoring, imminent failure can be identified and corrected. Conversely, without a sound monitoring program in place and subsequent corrective actions not being taken when needed, a single bearing failure can result in full machine shutdown and countless hours of lost of production. Bearing monitoring is guided by 3 main human senses: sight, sound, and touch. Bearing monitoring has typically been conducted through element observations. Fortunately, there are a number of highly sensitive tools that can be amplify these observations, making them more noticeable and recordable. They also included basic logic to assist it with warning identification. Hope you enjoyed this presentation. Namaste. Thanks for your attention. Please share your suggestions, feedback to my email ID kisagna@gmail.com.